Hello class, and welcome to chapter 9, which is about solving quadratic functions. We're going to do this chapter a little bit out of order. Section 9.3 is a really big section with a lot of information, and it's going to actually be useful for helping to learn the other sections in this chapter. So we're going to pull section 9.3 out and break that up into 3 different lessons. And then we'll have a mini test on section 9.3. And then after we're done with that mini test on 9.3, then we'll jump back into the rest of chapter 9 and look at 9.1, 9.2, 9.4, 9.5, 6, and 7. So we're going to start with just these 3 lessons from 9.3. We're going to have a mini test on that. And then the second half of chapter 9 will cover the rest of the sections. So 9.3 day 1 is going to be about simplifying radical expressions. And by the end of today's lesson, you'll be able to use the product property and the quotient property to simplify radical expressions. So a radical, which we should clarify, a radical is anything with a square root. So for example, if I wrote out the square root of 17, that is a radical because it has a square root. So anything with that square root sign is what we consider a radical. In order to have that be simplified, 1, it can't contain any perfect square factors. We'll go over what a perfect square is in a minute. And then 2, you can only have a radical in the numerator of a fraction. So if I have square root of 17 over 2, that's simplified. If I have the square root of 17 over the square root of 2, then that would not be simplified. So you can only have a square root, a radical, in the numerator of a fraction. So the 2 rules that we're going to be using to help us simplify these radicals are the product rule, which says the square root of a number can be broken up into 2 things that it can be multiplied by. So for example, if I was going to say I had the square root of 20, I could break that up into the square root of 4 times the square root of 5. So just like you can say 20 is equal to 4 times 5, you can say the square root of 20 is equal to the square root of 4 times the square root of 5. Our quotient rule says that if we're taking the square root of an entire fraction, we can break it into the square root of the numerator and the square root of the denominator. So if I'm taking the square root of 1/4, I can split that up into the square root of 1 in the numerator and the square root of 4 in the denominator to make it easier for me to solve. So we're going to use these 2 properties to help us simplify the problems. Another key thing that we want to make sure, I mentioned on that second slide with the rules, that we can't have any perfect square factors. So what that means is any number can't be divided by these perfect squares. Now what makes this list the perfect square? So for example, 1 is a perfect square because the square root of 1 is 1. Or 64 is a perfect square because the square root of 64 is 8. So perfect squares are the numbers where you can actually take the square root. So a number like 15, the square root of 15, that's not a perfect square. 15, you can't take a perfect square and get an integer answer. This slide right here shows the first 15 perfect squares. These are, again, ones you should probably have memorized. Beyond that, you can use your calculator to help you decide if a number can be square rooted or not. So that's numerical perfect squares. We also need to look at variable perfect squares. So for example, the square root of x squared is going to be just x because we have x times x gives us x squared. So if I want the square root of it, I'm breaking into its 2 factors, and that's just x. The square root of x to the 4th, the answer to that would be x squared. If I come down here to the square root of x to the 6th, that's going to give me x to the 3rd. So when you have an even number as the exponent, to find the square root, all you're going to do is cut it in half. So 2 cut in half is 1. 4 cut in half is 2. 6 cut in half is 3. If you have an odd number, we're going to use that product rule, and we're going to say that we can split it up into x squared and x if we have 3, because 2 plus 1 is 3. So we can take the square root of x squared, which is going to be x, and we can't take the square root of x because we don't know what number that is. If it was a 4, we could take a square root of it, and that would be great. But if it's 5, you can't take the square root of 5. So we're going to leave that square root of x because we don't know what value it has. Same thing can happen when we come down to x to the 5th. We can split that up into x to the 4th and x. So your job here is to pull out one of the x's so that you have an x by itself, and then that's going to get you down to an even number. So your square root of this one would be x squared times the square root of x. If we come to the 7th, we break it down, we take an x out, so I've got square root of x to the 6th, and then x. So I get x to the 3rd times the square root of x. So when it's an even number, you can just divide it, divide that exponent to get the square root. If it's an odd number, you have to pull out an x, and then you can take the square root. An odd variable exponent is always going to have the square root as part of its answer. So we're going to start actually solving some problems here. I've got the square root of 180. So my goal here is to see if any of the numbers from this perfect square list can divide 180. Obviously, 1 is on the perfect square list. 1 can divide everything. It's not going to help us. So I'm going to start with 4. And when I do 180 divided by 4, I get an answer of 45. So what that means is I can split it up into the square root of 4 times the square root of 45, because 4 times 45 is 180. Now that I have this square root of 4 out front, I can solve it. And the square root of 4 is 2. So I have 2 times the square root of 45. Now we know we can't take the square root of 45, but again we want to check that list. 45 can be divided by 9, which is another number on that list. So I've got 2 times the square root of 9 times the square root of 5, because 9 times 5 is 45. So now I can solve this square root of 9, which is 3. So I have 2 times 3 times the square root of 5. Now we all know that 2 times 3 is 6, so this final answer is 6 square root of 5. Why do we stop at the 5? Because 5 can't be divided by any number on that perfect square list. So we end up with 6 square roots of 5. Now, if we go back to this original problem up top here, 180, we check to see if it could be divided by 4. 180 can also be divided by 9. So we could have started the problem by splitting it into the square root of 9 and the square root of 20. If we had done that, we would have ended up with 3 times the square root of 20. But 20 then can be divided into the square root of 4 and the square root of 5. The square root of 4 is 2, which gives me 3 times 2, which again is going to give me a final answer of 6 square roots of 5. If I come back to the top one more time, 180 can also be divided by 36, which is another number on our list. So I could have started with the square root of 36 times the square root of 5. The square root of 36 is 6, once again giving us an answer of 6 square roots of 5. So there are multiple different paths you can take to solve these problems as long as you are always taking out perfect squares. Obviously, this last one is easiest because there's the least amount of steps, but they all get you to the same answer. Go ahead and try this one on your own. In this case, we can split it into 9 times 6, so we end up with 3 square root of 6 as our final answer. we have to do multiplication before we can even start solving the problem. You're going to go ahead and start by doing 14 times 2. So we've got the square root of 28. Now that is what we are trying to simplify. If you look back on that list, 28 can be divided by 4. So you end up with the square root of 4 and the square root of 7. The square root of 4 is 2. So we end up with 2 square roots of 7 as our final answer for this problem. Go ahead and try this one on your own. Multiplying, you're going to end up with 50, which can be split into 25 and 2, so you end up with 5 square roots of 2. Next thing we're going to do is introduce variables into here. When you have under the square root a product, so multiple things being multiplied, you're going to look at each element separately. So we're going to start with this 90. You look at your number list, and 90 can be split into the square root of 9 times the square root of 10. So we're going to split that up using our product property. Then we're going to come over to our first variable, which is x. This is an odd number here, so we're going to split that up. We're going to take out 1, which is going to give me 2, and then we're going to have our separate 1 in its own thing. Then we've got 4 y's. This is already even, so we know we can take a square root, so we're going to leave that one alone and leave it as y to the 4th. And then we come back to the last part. Z to the 5th is odd, so I'm going to say z to the 4th and z. So we split that up into an even and that extra 1. Now, when you are solving this, you are going to go through and look for the ones that you can actually take the square roots of. So you can take the square root of 9, that's 3. You can't take the square root of 10. You can take the square root of x squared, that's x. You can't take the square root of regular x. You can take the square root of y to the 4th, and that's going to be y to the 2nd, and then you can take the square root of z to the 4th, and that's going to be z to the 2nd. So all of the numbers that we can take the square root of, 3, x, y squared, and z squared, we solved those pieces, so those come to the outside. The leftover parts, the 10, the x, and the z, are going to stay on the inside of the square root, so the square root of 10x, and then that should be 10xz. So that is our final simplified version of the original problem. We took out any perfect squares that we could and solved for them, which is how we got the outside part, and anything that wasn't a perfect square stayed on the inside. Go ahead and try this one on your own. So we can split 32 up into 16 and 2. You also could have started by doing 4 and 8 and then splitting 8 into 4 and 2. Either way, that final square root here for the number is going to be 4 on the outside and 2 on the inside. R squared is a even, so that stays. K to the 4th is even, so that stays. N to the 5th, you split up between n to the 4th and n, giving us a final answer of 4rk to the 2nd, n to the 2nd, square root of 2n. Now we're going to get into that fraction part. That was that second rule that we had that says square roots can only be in the numerator. So we're going to use our quotient rule here, and we're going to split this up into the square root of the top, so square root of 17, over square root of 9. Now we have a square root in the bottom, but as you notice, that's a perfect square. So we can go ahead and solve that, and the square root of 9 is 3. So our final answer here would be square root of 17 over 3. So we have just a regular integer in the denominator, which means we are done solving the problem. Square root of 17 can't be simplified anymore. Go ahead and try this one on your own. Split it up, top and bottom. You can take the square root of the denominator, which is 7, so you end up with square root of 21, which can't be simplified, over 7. Now we're going to talk about what we can do to rationalize a denominator, so to get a square root out of the bottom. So if I split this up, I'm going to end up with square root of 35 over square root of 15. 15 is not one of my perfect squares, So I have to do something to get this out of the denominator. The first thing you want to look at is see if there is anything in common between the numerator and the denominator. That's going to help you reduce the fraction. So our goal here, we've got 35 and we've got 15, which means we can reduce that fraction by dividing by 5. So what that means is you've got the square root of 7 over the square root of 3. So if you can reduce the fraction, you should reduce the fraction just like normal. After that, we still have a square root in the bottom. We can't have that here. So what we're going to do is something called rationalizing, which means we're going to multiply the top and the bottom by whatever is on the bottom. So we're going to multiply both the top and the bottom by the square root of 3, because 3 was on the bottom. So what that then does is puts us at square root of 21 on the top, because 3 times 7 is 21, and square root of 9 on the bottom. Now we have a perfect square on the bottom, something that we can solve. So our final answer here ends up being square root of 21 over 3. So again, to rationalize, you need to multiply the top and the bottom, numerator and denominator, by whatever was in the denominator, and then continue to simplify. So we got 21, square root of 21 over 3. Again, we can do this same process with variables. So I'm going to start by splitting it up. I've got 6y as a square root in the numerator and square root of 12 in the denominator. Can't take the square root of 12, so I look to see if I can reduce it. My answer is yes. 6 and 12 can both be divided by 6, so I'm going to go ahead and divide them both by 6. So I'm going to end up with the square root of 1y, or just y, over the square root of 2. Again, still can't take the square root of 2, so now I need to rationalize that denominator. So I'm going to multiply the top and the bottom by the square root of 2. And up top, that's going to give me 2y inside of a square root over the denominator, which is going to be square root of 4. Now I can take the square root of 4, which is going to give me 2. So I'm going to end up with a final answer of the square root of 2y over 2. So again, when you rationalize, you are multiplying by whatever is on the bottom. Go ahead and try this one on your own. So we split it up top and bottom. We can reduce both by dividing by 8. We're going to multiply then by the square root of 3 to rationalize, and we end up with the square root of 3b over 3. If you have questions about this or anything else from the lesson, please let me know when you get to class.